I'm Paul Ducklin, as usual on Friday on Naked Security Live. You can probably guess what this week's video is going to be about. It's the only picture I've got for this week, but if you want to find the article on nakedsecurity.sophos.com that we already published about this, it has some great technical detail about it. That's what you should look out for when you get to the website. Zerologon. So just look for the big red rectangle with all the zeros behind. I've got add when hi. Jody Staples, yes, thank you, Jody. I'm assuming yes means yes, you can hear me. Great. So the Zerologon story, it's been all over the news this week because it is a way, in theory, that an attacker could log in, if they're already on your network, that they could log in or they could get access to your domain controller, the thing that controls all the passwords on your whole network, and set its password to blank. They couldn't log in with a blank password after that, but they could do a trick that lets them think it has a blank password. They could use that to extract cryptographic secrets from the domain controller with which, with a bit of luck, they could break in, subsequently log into the domain controller and basically take over entirely. And if you run a Windows network, you'll know that if the crooks can log into your domain controller as an administrator, then pretty much they control your whole network. Now the good news is that this Zerologon bug, it was patched by Microsoft in August 2020, and everything we'll talk about in this video about how crooks can use this against you doesn't work anymore if you've applied the patch, so far as we know. Nobody has found a way around a patched system, so if you haven't patched with the August patches and you run a Windows network and you have unprotected servers, please patch now. You've already had a month. That should have been long enough. This patch was, although Microsoft understandably didn't give away any details, it had a security rating of 10 on a scale of 0 to 10. So when you get severity rating 10, it means we think this is kind of important. So if you haven't patched, please do. You need to do that to protect yourself, but you also need to do it because if you're not doing it, crooks can take over your network, and that means you could be used as a jumping off point to attack someone else. So if you're not prepared to do it for yourself, at least do it for everybody else. Sumit Sharma, loud and clear, thank you. Excellent. I'm glad that it's all working. So let's look at what happened in this Zerologon problem. What happened is after Microsoft announced this fix, a Dutch security company figured, well, let's look into this. It sounds kind of intriguing. NetLogon is the protocol involved. That is the protocol that you use between a client and a Windows server. In fact, it's an open specification now, so you could either implement your own NetLogon client if you want to interoperate with Windows servers, or you could build a Windows-style domain controller authentication server system using the protocol. But basically, if you want to do client-to-server connections to a domain controller, for example, or a Windows server, and give it commands like, hey, I want to change my password, you're almost certainly going to be using this NetLogon protocol. So it's kind of fundamental to managing passwords, amongst other things, on Windows networks, to controlling how you log in. So Secura, the Dutch security company, thought, if there's a very severe problem in this, let's try and find out more about it because it's a little bit of a mystery at the moment. Michael Stevens, I'm wondering how anything AES messes with Windows when feds own Windows and use AES it by NSA standards. Oof. Not quite sure what oof means. Let's get on to that. It was a cryptographic mistake. I don't think anyone did this because they were told to by any organization. It was there in open text. It's been there for years. It's in the specification. The Secura guys discovered what the problem was. Basically, when you authenticate from a client to a server using NetLogon, the encryption system that is usually used, which is supposedly the modern version, is going to be AES 128. That is a perfectly respectable encryption algorithm. It has no known vices, no known statistical biases. Everybody should use it because it's the one true way to do encryption these days. So Microsoft figured, let's use it, and let's use it in a mode called cipher feedback mode. That's a special way of using AES where you don't where when you encrypt the same thing over and over again, you don't get the same output. So it gives you a little bit more disguise, and it's a normal way in which people would use this encryption algorithm. Now, when you use this, these so-called feedback modes with AES, or any block cipher for that matter, you don't just need an encryption key, which in the case of AES is 16 bytes long. You also need a thing called an initialization vector. You'll often hear it in the jargon called a nonce, which is short for number used once. Note that, number used once. It's supposed to be a random value that's agreed by both sides. It doesn't have to be secret, it just has to be random, and it has to be different every time you use the same key. And the key comes, your computer will have it in its registry, carefully hidden by Windows. The domain controller will know it. So the key is known only to the two ends of the conversation. That's the theory. And then to kickstart the encryption, you need to put in this thing called the initialization vector and the NetLogon protocol. You can understand why if you read the article. It also requires each end, the client and the server, they swap two 8-byte random numbers. So what you get is a secret key, a shared secret that each end has. So if you're an attacker, you already need administrative access on a computer if you want to figure out what that key was. So the Dutch guys figured, well, how could this work if you don't already have access to a computer? How can you negotiate this protocol if you don't know, or if you don't know the one important thing, which is the shared secret, the secret key? Now, what's supposed to happen is you would have these two 8-byte random values chosen by each side. You'd have a 16-byte random initialization vector chosen by one side or the other and agreed upon, and the secret key. And with all of those bits of source, you should be able to log in as a client to the server, and the server will know that you know the password and it will let you in. Unfortunately, in the Microsoft specification, there's a thing that says use an initialization vector of all zeros. You are not supposed to do that. Like I said, the whole idea of an initialization vector or a nonce, it is a number used once. You are definitely not supposed to use the same initialization vector ever with the same encryption key, and it will be the same every time you log in because it's your computer's password, because otherwise you'll get the same output from the encryption cipher every single time, which would be useful to an attacker watching. So what these Dutch guys discovered is, in fact, if they fed, remember that the two sides are supposed to exchange random numbers, there's a random initialization vector and there's a secret key. Now the initialization vector is already randomly compromised because it's all zeros, a bit worrying in a cryptographic context. The server would supply a good quality 8-byte random number, but the Dutch fellows discovered that if they supplied their random number at the beginning, if they supplied 8 bytes of zeros, combined with 16 bytes of initialization vector zeros, combined with the secret key, combined with 8 bytes of server randomness, by having all those zeros in the mix, because the initialization vector is not random enough and their random bit is not random enough, then 1 in every 256 times they tried to log in, they would actually put the cryptographic engine into a mode in which an all-zero input would always produce an all-zero output. In other words, for one special type of input, they knew how to encrypt it correctly, even though they didn't need the key, but only 1 in every 256 attempts. So it doesn't sound like much, but as we'll see, that was the wedge that allowed them to take over your domain controller. Michael Stevens, NSA. I don't want to get into NSA backdoors in Windows here. I think that's a bit of a red herring in this case. In this case, the problem is that Microsoft's specification had a cryptographic shortcut, set the initialization vector to all zeros as a convenient way so the client and the server didn't have to exchange an initialization vector initially, and that's what led to the flaw. So I don't want to go down the rabbit hole of backdoors. I don't think that's relevant here. So the deal is that these guys figured out a way that 1 in every 256 times they tried to log in, they would get the encryption channel into a mode in which, as long as all they had to provide was an input that was all zeros, they would be able to encrypt it correctly because they could know that it would come out as all zero. If there was a single bit or byte in the input that they had to provide that was not 0, any one of them, they wouldn't be able to do the encryption. So they had this tiny little sliver of hope that they might be able to trick the other end. And they found it. They discovered that there is a password reset function provided in the Zerologon protocol specification in which they are required to provide 2 correctly encrypted inputs. One involves the number they applied originally, which was a load of zeros, plus the current time in seconds since the beginning of what's called the Unix epoch, 1970. So that number at the moment, it's somewhere around 1.6 billion. So you can imagine when you add 0 to the current time, oh dear, you don't get 0. So they thought, well, we're stuck. We can't come up, we need a 0 in input that's all 0, because only then do we know how to encrypt it. It comes out as all zeros. So they thought, well, let's see if Windows cares if we just pretend it's 1970 all over again. So they put on their flared trousers and they sent in the authentication request saying, it's the 1st of January 1970. And the server went, okay. The next thing they needed to do is they needed to provide a big block of data, 516 bytes as it happens. You can read why in the Naked Security article, that contained the new password plus the new password size appended together. So, the comment there from Jed, I don't quite understand what he means by that, so I'll let that go. Okay, so they've got this password log and says we have to provide 2 bits of encrypted input, and the only way it can possibly work is if the encrypted output that they need, the input they provide, is all zeros. So they need to have a timestamp which is supposed to be about 1.6 billion. That's a 32-bit number with that in it, but they found 0 would do. 1st of January 1970, and they needed to provide a block containing the new password in which one of the fields was the length of the new password. So they had no choice but to try and set a blank password length 0. And they kind of figured, well, the server's not going to allow me to have a 0 length password, but it did. So that's why it's called Zerologon. It involves feeding far too many zeros into the sort of encryption mill so that it can get stuck in a mode where when it's encrypting 0, it always gets 0 as the output. It kind of gets locked in. We've made a little diagram and a video on the Naked Security article which clearly shows why that should happen. And then they discovered a password reset function where it was possible for them to use inputs that were only and all bits that were 0 by pretending it was 1970 and saying, I want a password with length, wait for it, 0. And unfortunately, the server would accept that. So it was, if you like, a compounded series of errors. A cryptographic shortcut involving an all-0 initialization vector. The server not reliably checking the timestamp. Now, we don't know why the server didn't find it suspicious that it was 1970. One guess might be that they didn't want to prevent devices that didn't have a real-time clock and couldn't set their time in advance from logging in. Any enthusiasts out there, if you've got a Raspberry Pi, you will know that the one thing it lacks is a real-time clock. So every time you plug it in and power it up, it thinks it's the 1st of January 1970. And why they allowed you to set a 0-length password, I guess they figured, well, you have to have authenticated anyway with an existing password, but of course in this case these guys had one and only one way to do encryption correctly without knowing what the original password was. So that's how the bug works. And basically the way you fix it is you go out and you get your August 2020 Microsoft patches. That way, as far as we can tell, the bug is fixed. In fact, if you read through the protocol specification, which was updated in August, you'll see that at least one of the things Microsoft has done is that they no longer accept that initialization string that's provided by the client at the beginning being all zeros, or even any byte repeated too often. So in other words, they check that there is enough randomness in the system to avoid the fact, because obviously they can't say, oh well, we'll change the initialization vector, because every client in the world would then need reprogramming and updating. So they're sort of between a rock and a hard place. But it seems that they have provided a mitigation which will stop this. So I'm going to go through my 4 tips. Actually, there are 5 tips because one of them's so important I'm going to do it twice. And so some of this is advice for programmers who are implementing protocols like this, and the other is the advice for the rest of us. Before I do that, let me say, if you're somebody at home and you don't have a Windows network and you don't have a Windows domain and a Windows domain controller, well, you still need to get your August patch and your September patch, because there are loads of other fixes in there that are important for you. But really, the big deal in this is if you're on a network where there's a Windows domain controller, because that's what the crooks are after. Because the domain controller is what looks after security and manages logins for your entire network. So a hole in the domain controller is kind of a hole in your home network, in your whole network. So here are the tips. You've heard the first one: patch early, patch often. If you'd patched in August before all this research was done, and unfortunately, I can only call them clowns. They're all over the internet now. A whole load of people have taken that research, like we did at Naked Security. Instead of just writing it up and explaining it, they've gone, hey, we'll make a working exploit and we'll write it in Python, and wouldn't you love to be able to download it? Look, now you too can break into any network you like. So unfortunately, there are working exploits circulating freely on the internet now, which makes it really important that you patch, because unfortunately, every time there's news like this, there are people who can't resist going that one step further than just saying, we know this works and you can see why it works. They have to go out of their way to prove it too. So that's the first tip. The patching is important. The second thing, if you're a programmer, if you're doing anything involving cryptographic stuff, don't take cryptographic shortcuts. Microsoft did here. They just said, set the initialization vector to 0. There's enough randomness coming in from elsewhere. She'll be right. But unfortunately, that's not what happened. Somebody found there was a way by adding zeros elsewhere into this equation that they could actually cause everything to fall into this abusable or exploitable mode. The second thing, if you're a programmer, my third tip is be really defensive about potentially dangerous data. If you're requesting somebody in a protocol to send you some kind of authentication token in which you expect them to build in the current time, presumably what you're doing is you're trying to prevent replay attacks, which is where someone takes a token from yesterday or last week or last month or 1970 and tries to use it all over again. It's kind of like changing the lock when you move into a new flat. You think, I don't know who's got the keys to the last one. If I start afresh, I'll be all right. And so if you've got something that's trying to test somebody by getting them to say, here is the time on my computer, how does it line up with yours? Then don't just ignore that data if it's actually giving you a warning that something went wrong. To be honest, if some client is trying to connect to you and you're asking them to put in a timestamp and they put in 0, which says it's 1970, the most likely thing, assuming they're not a crook, is that they've got some kind of initialization or programming startup problem in their code. So just say no before you start, and you'll, in the same way also that when you're saying, I would like to set a new password and I would like this password to be, well, actually, I don't want one. Just set me a password of 0 bytes. There's no need for that. Windows already has a secure way of storing passwords locally and centrally in a secure way. It's encrypted in the registry on the client and managed by the Active Directory database on the server. So even for computers that never have a human logging in, that never have somebody to actually sit and type a password, there's no need for any device to have a 0-length password, because Windows computers have a way of deciding that the other end has a proper password anyway. So there's no need to have 0-length passwords as valid passwords. And the third thing, the fourth tip, the third thing if you're a programmer, move with the times if you possibly can. So if you look at them, now unfortunately for Microsoft here, this is one of the newer parts of their protocol where they've introduced AES instead of using DES or DES, which was the old school cryptographic system that came ironically from the 1970s. So although they'd moved with the times, the problem is, and I get why they did this, it's because they need backward compatibility with millions of different devices and lots of older versions of Windows. But the specification is 280 pages long. Now, if you've ever done Bluetooth programming, comparatively that's quite short. But there's an awful lot of stuff in there that's in there because it's just kind of stuff that's accumulated that people are supposed to be moving away from. So when you're programming, particularly when there's cryptography involved, if you're taking a step forward, try and leave the past behind. Otherwise, all you're doing is creating a protocol or a specification that's really far too difficult for anybody to be able to take in all at once. And then what happens is we found out something is bad because somebody finally just looks in the wrong place at the right time. So let's go through the tips again. Obviously, patch early, patch often. If you're programming, do not take cryptographic shortcuts like saying, oh, let's dispense with the initialization vector. We don't really need it. Be defensive when you're getting data that already tells a bad story, like when it's 2020 and someone's trying to convince you that they think it's 1970. They're probably up to no good. And lastly, when you move ahead, try and leave the past behind you. We've seen that in spades, unfortunately, in the web, where we still have websites that use ancient encryption technology that leave themselves at risk, and we don't dare kill them off because they're kind of considered important. And somebody needs to take the step to move forward and leave the past behind, because cryptography gets better and unfortunately attacks get better. So thanks for listening, folks, and until next week, stay secure.